Well, this is section 4.5, moments about a specified axis. Well, we've talked about two-dimensional moments, and we recognize that two-dimensional moments are either counterclockwise or clockwise, and that would be positive or negative. We've also done three-dimensional moments about a point using the cross product, R cross F. Well, the thing to recognize is that all objects are actually three-dimensional objects. All objects are three-dimensional objects. Sometimes we will look at them as two-dimensional objects for convenience, and that helps us simplify things, but to recognize that all objects are actually three-dimensional is an important concept. The same thing is all moments are actually three-dimensional moments. However, we will sometimes simplify them and look at them as two-dimensional moments for convenience. But in all cases, if there's a point of rotation in a two-dimensional way, in a three-dimensional way there is actually an axis of rotation. Alright, so let's look at this man that's trying to rotate this screw here, or this nut, whatever that is, going into the engine. He's trying to push on it with a force here. There's a lever arm right there. There's going to be a moment in this direction. That would be a counterclockwise moment, which would be a positive moment. In a two-dimensional look, this is going to be the point of rotation. However, if we look at this as a three-dimensional object, this is going to be the axis of rotation. It'll be rotating in this direction, and the axis of rotation looks like that. By the right-hand rule, if it's rotating in this direction, the thumb is the direction of the moment, which actually comes out of the page. If I were to redraw this on a three-dimensional grid, I could say that this is the x-axis, the y-axis. So I've just redrawn it over here, where this is the x-axis, the y-axis. I'm going to push on it with a force. It's got some lever arm. It's going to rotate in this direction, rotate in that direction. That's counterclockwise, which would make that a positive moment. What we can see is that it rotates about the positive z-axis in this direction. I'll put a little circle like this. It'll be rotated in the positive z-axis. And what that means is that by the right-hand rule, if I were to rotate in this direction, this makes this a positive z moment, positive z. And that's what we've defined by the right-hand rule too, right-hand rule, positive z. All right, let's look at this, this crowbar down here. Same kind of thing. If we could look at this as a two-dimensional situation, it rotates about point O. However, if we look at this as a three-dimensional situation, it actually rotates about this axis. We're going to assume that this force dominates, so that this is going to be the moment about this axis. It'll be that force times this lever arm. By the right-hand rule, if it rotates in this direction, which would be in this direction, rotates like that, then the axis of rotation would be in this direction, and that would be a positive rotation in that direction, that axis. Obviously, this two-dimensional look of a wheelbarrow is a simplification of a three-dimensional situation. It clearly is a three-dimensional object, and if we look at this as two-dimensional, it rotates about that point. However, if we look at this as a three-dimensional object, then it rotates about that point as an axis. If it rotates in this direction, it would be rotating about the axis going through that axle at A. Alright, well we've talked briefly about this picture before, that this as a three-dimensional object, this is a tree, this tractor's trying to pull it in this direction. It's actually trying to bend it about this axis. So this would be the axis of rotation. Because the bending is trying to go in this direction, trying to go like this thumb is going to, this will be the direction of the moment, and that's also helps be defined by that thumb. In other words, if I try to pull it in this direction, rotate it in this direction, the thumb defines the maximum, or defines the direction of the moment. Now this one is not quite so easy. Sometimes the axis is easy to identify and understand. Sometimes the axis isn't so easy to identify, and we'll have to do a little more work. So in this case, I can see that this force here is trying to cause some rotation about the z-axis. However, there's also going to be some rotation about the y-axis, and possibly some rotation about the x-axis in the same way. So again, it's hard to see sometimes. Sometimes it's easy to see the axis of rotation, sometimes it's not. But in this case, we would have to do a little more work to discover the axis of rotation, but I'm going to guess that it's going to be predominantly trying to go that way, and that the axis of rotation is something going in this direction, and that would be defined by that right-hand rule and the thumb.
Well, what I have here is a little demo of rotation about the x, the y, and the z-axis. So I have a little shoebox here, and I'm going to apply some forces, and you're going to see the rotation, I hope. So let's apply a force right here. And if I did that, it would have a tendency to rotate the box about the x-axis. The force times this lever arm would cause this kind of rotation. So the magnitude of the moment about that axis would be the force, magnitude of the force, times that lever arm. It doesn't really matter if I apply the force here, or here, or here, or here, here, or here. In all cases, the force times that lever arm is going to be the magnitude of the moment. The direction of the moment is determined by the right-hand rule. So if I rotate in this direction by the right-hand rule, I'm rotating in this direction. The thumb is defining the direction of the moment, so this would be in the negative x-axis. That rotation would be in the negative x-axis. All right, if I were to apply a force here, I would have this lever arm, which would try to rotate it about the y-axis. That force times this lever arm rotates about the y-axis. Again, it doesn't matter if I apply the force here, or here, or here, or here. In all cases, the moment is going to be in this direction. It's going to cause rotation in this direction. The magnitude of the force times that lever arm. The direction of the moment, again, defined by the right-hand rule, is trying to rotate in this direction. So this would be in the negative y direction. That's positive y. This would be negative y. All right, one more. Let's say I apply the force here, and it's going to try to cause some rotation about the z-axis. The magnitude of the moment is the force times this lever arm. And again, it doesn't matter if I apply the force here, or here, or here, or here. In all cases, the lever arm is going to be the same. It's going to try to rotate it in this direction. The direction of the moment is defined by the right-hand rule. So this would be in the positive z-axis as it's trying to rotate it around. If I were to apply the force in this direction, it would cause rotation in this direction, which again would be the negative z-axis.
Well, let's use our little shoebox demo here and put some real numbers and some dimensions in here and see if we can find out the magnitude of some moments about the specific axes. So first of all, let's define our axes. So I have this as x, y, and z. Go back to black here. And let's put a force on here. The first force I want to apply is a force right on that corner going in this direction. I'll call that F1. Let's say that it is a magnitude of 10. Let's also look at the dimensions of the box so we can get some lever arms. Let's say that this dimension is 2, and this dimension is 3, and this dimension is 4. Okay, I'm going to build a little matrix here. I'm going to call this F1 is equal to 10, and it is going in the positive j direction, so that would be 10j. What I want to do is take each axis independently and find out the rotation about that axis using some rules which we're going to describe. Alright, let's consider first rotation about the x-axis caused by F1. By our little demo that we just watched, this force times this lever arm is going to be trying to go in that direction. By the right-hand rule, if it's rotating in this direction, that would be the negative x-axis, rotation like that. So let's go ahead and put that into our box. So I'm going to say that this is going to be negative 10 times the lever arm of 4. Now, how about rotation about the y-axis? What we're going to find is that any force that is parallel to an axis has no moment. So forces that are parallel to an axis have no moment. So I'm just going to put a little parallel sign there to say that that is 0 moment. About the z-axis, any force that goes through an axis also has no lever arm. So any force that goes through an axis, and this goes through the z-axis, there's no lever arm, so I'm just going to put a T here to say that that is through the axis. Alright, let's consider another force. How about F2? I'm going to go down like that, and we're going to say that has a magnitude of 3. Let's go ahead and put that in my little matrix here. F2 is equal to negative 3k. Alright, how about moment about the x-axis? It does have a rotation, a tendency to rotate about the x-axis caused by this force times that lever arm. It's going to be going in this direction. It's going to try to rotate in that direction, so this would be a positive moment about the x-axis. So it would be 3 times 2 in the positive x. Sorry about that. Hit the wrong button. Alright, how about through the y-axis? Or let's talk about rotation about the y-axis. You can see by transmissibility that force goes actually through the y-axis. This is the extension of the y-axis, so we can say that there is no rotation about the y-axis. That will be through. About the z-axis, we have the force is going to be parallel to the z, and because it's parallel, there is no moment caused about the z-axis. Let's try another force. How about F3? And apply it right on that corner, F3, and let's say that it has a magnitude of 5. So let's put that in my matrix, F3. In this case it is 5 going in the negative x direction, so it would be negative 5i. Alright, by our rules again, if it is parallel to the x-axis, that means there is no moment. If it goes, okay, how about the y-axis now? In this case it has a force times this lever arm, and again by transmissibility I can apply that force back here, times this lever arm. It's going to have that direction, which would be in the negative y direction, so it would be 5 times 4 in the negative y. How about through the or around the z-axis? Again, it's going to have, by transmissibility, I can move it back here if it's easier to see. That force times this lever arm is going to have some rotation in this direction. By our right hand rule, that's going to be in the negative z-axis, so that would be negative 5 times 2. Alright, so we're making a compilation of all of the moments caused by these three forces in the x-axis, the y-axis, and the z-axis. Now I'd like to add one more that's just a little more complicated. I'm going to say that there's a force here, call it F4, and that's going to be equal to have a magnitude of 4, and it's going to be in this plane. So I'm going to say I'm going to draw the line of action, and it's actually going to go right through this point, right like that. Okay, you can see that it is in the XZ plane. There is no component in the y-axis, so let's draw the two components then. I'll say that there's going to be a force going down this way. I'll say that that is F4Z, and there's also a force in the x direction, and I'll call that F4X, like that. Okay, let's look at the picture and try to figure out some of the magnitudes of that force. If you can see here, maybe it's obvious, but this is going to be a 3, 4, 5 triangle. So I'll go ahead and put that 5 right there on that diagonal. Now what I'd like to do is break that force up, this force up into its two components and evaluate them independently. So let's go ahead and move this up just a little bit. I think I have to zoom out a little bit so I can get it all in. There, I think that'll work. Okay, let's draw the two components. So this will be F4. Let's say F4x. What is the magnitude of F4x? Well, if we look at this, this will be the 3/5 component of 4. So that's going to be 3/5 times 4. And if it's parallel to the x-axis, which it is, there's going to be no moment. If it is going through the z-axis, which it is, there's no moment. However, it does cause some rotation about the y-axis right here. And so that would be the moment, or that'd be the lever arm, so it'd be F4x times 4. So let's go ahead and put that in there. And the direction would be positive because it's trying to go in this direction. That would cause a positive moment. So that would be equal to 3/5 times 4, whichever that is. And the lever arm is also 4. And there we have that. All right, let's look at F4z now. F4z, and the magnitude is going to be the 4/5 component of that 4. But let's look and see what happens here. It is going straight down, which means it's going through the x-axis. It's also going through the y-axis, and it's also parallel to the z-axis. So there's no moment at all caused by that component of the force. So to add them all up, that's what we want to do. We add each of those independently, and we can find the moment about the x-axis is equal to -34. The moment about the y-axis is equal to -11.4. And the moment about the z-axis is equal to -10. If we want to find the moment about point O, which is the origin, we add all those up. And it's very simple and very easy, and this is something that you'll understand as we move. But the moment about O is equal to -34i, -10 or 11.4j, and -10k. And that's going to be the moment about the origin. Well, the next thing we want to do is look at this force applied at the end of a bent pipe and find out what the magnitude of the moments is about each of the 3 axes. We're going to go just a little bit faster since you know the system now. So let's look at our axes first. Let's say that that is x, y, and z. And let's say that this force is equal to 100. And again, we're not going to focus too much on the units. You can call it newtons, you can call it pounds, whatever you'd like. Let's put some dimensions here. Let's say that this is 3 and that is 1. And then you can see how the force is pointing up to a point on the wall. So let's put some units on there. Let's say that it's going 4 and 4. Alright, so the first thing we want to do is define the directions of the components of the force. And I like to draw them right on the picture. And if you can recognize this, recognize there's going to be a force in the x direction. There's going to be a force in the y direction. And a force in the z direction. And that's really helpful to visualize that if you can. Draw that again. Now let's go ahead and define the force. And what I want to do is go back to our unit vector concept and say that I want to go from here. I'm going to go positive in the x, negative in the y, then I'm going to go negative in the x, and then positive in the z. And you can see how to get there, and I will just go ahead and write down the unit vector for you, and then you can follow along. Okay, so I've written down the force for us, and you can see that it goes 3 in the I, negative 3 in the I direction, negative 3 in the j direction. So negative 3 in the I direction, negative 3 in the j direction, positive 4 in the k, and then it's 100 newtons or 100 units, and so here's going to be the Cartesian description of our force. Okay, let's talk about those 3 components and what their individual moments are about the three individual axes. So I'll go ahead and put Fx, Fy, and Fz here about the x, the y, and the z axis. Alright, let's look at force in the x direction. Force in the x direction is parallel to the x. The force in the x direction has no moment about the y because it's through, and the force in the x direction has this lever arm about the z-axis. That is going to be in the positive z-axis as it's trying to rotate here by the right-hand rule. It would be positive z. So let's go ahead and write those down. It's going to be parallel to the x through that, and it'll be 51.4 times 3 will be the magnitude in the positive z-axis. Alright, and the force in the y. Force in the y is parallel to the y-axis. Force in the y goes through the x-axis, but the force in the y has this lever arm about the z-axis. Positive, so let's go ahead and put that in there. It's going to be through the y. Beg your pardon, this keeps getting the wrong pen. Let's go through the y-axis parallel, or sorry, through the x-axis parallel to the y-axis, and our magnitude is 51.4 times 1 about the z-axis. Similarly, the force in the z has going up like this. It's going to be parallel to the z-axis. It's going to have a positive moment about the y-axis caused by this lever arm, and about the z-axis it'll have this lever arm. Again, going positive that way. So let's go ahead and put all those things in there. Then you add all those up. I'll go ahead and push this up just a little bit, and we can say the moment about point O is going to be equal to and that's going to be the moment about point O, but it's also the individual moments about each of those three axes.